So, what is a space link? What is required for that? What happens? What happens if the space link is not there? Okay, first I will define what is a space link is. A space link is a connectivity between the satellite in space and the Earth station in Earth. So the connecting the space link plays a major factor in satellite communication. Why? Because the Earth station transmits signals to the satellite for observing a particular location or a point or a geographical area, or in order to transmit signals using a frequency called uplink frequency. Then these signals which reaches the satellite in space are being processed or amplified or repeated or magnified or boosted by using some amplifiers. Most probably we will be using your TWT amplifier processing, and it is being sent to the earth back. Satellite will transmit it back to the earth at a remote place or at a farther distance from the transmitter, and the same signal which has been transmitted can be obtained from the satellite to the receiver, which we call it as downlink frequency. The uplink frequency is from satellite transmitter, from earth transmitter to satellite, and from the satellite to the receiver, the frequency used is your downlink frequency. Always the uplink frequency will be higher than the downlink frequency. So for this space link design, what is required, or what are the basic necessary information is that calculating link power budget. Link power budget. So what is a link power budget? Is that a link budget is accounting of all of the gains and losses from the transmitter through the medium. So transmitter will be present in the earth station, from the transmitter to the receiver, whatever the gain and losses occurring due to the transmitter and receiver in a telecommunication system, along with the considerations of channel. So the channel is your medium, where it could be a free space, a cable, a waveguide or optical fiber, or anything else, or a conductor, whatever we use it for channel. So a channel connects your transmitter and receiver. So all the gains and losses accounting due to this is called as a link budget. So we need to calculate these two quantities. So the first quantity is transmit power and the receiver power. Okay. So these are the two quantities to be calculated for link budget calculations, which are measured in decibels. So the first such link budget calculation is EIRP. So most probably everyone would have studied antennas. So in that we have a parameter called EIRP. Okay, so there is a change. There is a typing error. Let me change it. Equivalent isotropic radiated power. It lays as a P parameter which is defined as the maximum power flux density at a distance from the transmitting antenna of the gain. The maximum power flux density at some distance from the transmitting antenna. So which can be obtained by the formula phi m is equal to G PS divided by 4 pi R square. Maximum power flux density at some distance. So that distance could be your receiving, or that distance could be your satellite's distance, or the distance could be your booster, or it could be a repeater in between. So the maximum power flux density at that distance from the transmitting antenna is called as equivalent isotropic radiated power. In short, EIRP. So flux phi m is equal to G PS divided by 4 pi R square. R is the distance, G is the gain of the transmitting antenna that we are using, and PS is the transmitted power. So an isotropic radiator with an input power equal to a GPS signal or equal to a GPS transmitter would produce the same flux density. Hence, the product is referred to as an EIRP for an isotropic radiator. So it is always expressed in decibels, as said earlier, relative to 1 watts or decibel, 1 decibel watts. So EIRP is equal to G into PS. So gain is measured in decibel watts. So dB watts. PS is the power in the transmitter. So measurement is EIRP is equal to PS plus G. So we have an problem based on that. The question is, a satellite downlink operating at 12 gigahertz with a transmitting power of 6 watts and an antenna gain of 48.2 decibels. So calculate EIRP in decibel watts. So always we should take in terms of the equation for only 1 watt. Okay, ERP is often expressed in decibels related to only 1 watts. So 10 log 6 watts divided by 1 watts plus the gain 48.2. So we get 0.2. We get 56 decibel watts in decibel watts. So this is how to calculate PL. Next is that we are going to calculate for a parabolical antenna. Here we are seeing for an isotropic antenna. Now we are going to see for a parabolical antenna. Okay. So we are going to take the equation of G. So G is equal to eta into 10.472 FD the whole square, where eta 1 is pi d by lambda the whole square. Okay, where F is our carrier frequency in gigahertz, D is the reflector diameter in meters that we are using for parabolic fashion, and eta is the aperture efficiency. So always the aperture efficiency is considered to be as a nominal value which is derived by Andrews antenna, who has designed the antenna in 1985 as 0.55. Typical value for aperture efficiency is 0.55, although it could be higher for some of the cases as 0.73. So normally we choose 0.55. So 0.55 into 10.472 FD the whole square. So when we manipulate that, we get G is equal to eta 3.192 FD the whole square. So based upon this, we are going to solve a problem. So the question is calculating the gain in decibels of a 3-meter parabolic antenna operating at a frequency of 12 gigahertz. Operating at 12 gigahertz. So assuming the aperture efficiency of 0.55. So 0.55 into 10.472 in the previous case is this 10.472 into F is 12 gigahertz into D is your 3 meter. So substitute, simplify, and check whether you're getting the power gain. Power gain is 78168. So 10, take 10 log of this in order to find it in terms of decibels. So you get 10 log 78168, which is 48.9 decibels. So this is the gain of the EIRP for a parabolic antenna. So these are just two problems based upon the first parameter or the first link budget calculation. So any queries you can type in chat box. If you have any queries, you can type in chat box. Then I'll proceed for the next design consideration. So since there are no queries, so I'll proceed for the next parameter, which is transmission loss. So power is applied at one end of the transmission link. Due to various losses, the power received at the other end will vary. For example, if we send 100 watts of power at the transmitter, the same 100 watts of power will not be obtained at receiver due to the channel losses. Okay. So atmospheric radiation, space consideration, celestial bodies in between, other satellites in between, distance, distraction, and so many factors. Okay, so that we are going to see. One of them is the transmission loss. So these losses are mostly depend upon the rainfall. So as a first step in the loss calculations, the power loss resulting from the spreading of the signal in space must be determined. So this calculation is similar for the uplink as well as the downlink of satellite circuit. So let us see the first transmission loss, which is free space. The power flux density at the receiving antenna can be obtained by phi m, which is EIRP divided by 4 pi r square. So now let us substitute that EIRP. EIRP is your value that we had seen. Okay, so that we are going to substitute it here. So the power delivered to the matched receiver is the power flux density multiplied by the effective aperture of the receiving antenna. And the received power is PRA is equal to phi m A effective aperture of that particular antenna. It could be an isotropic, it could be a directional, it could be a parabolic. Any examples can be taken into consideration, depending upon the necessary and a need of service being considered in the satellite. So phi m effective aperture of the receiving antenna. So the received power will be EIRP divided by 4 pi r square, which is phi m or flux density, into effective aperture of the antenna, lambda square GR divided by 4 pi. So on simplification, we get EIRP, gain in the receiver GR, lambda divided by 4 pi or the whole square. The transmit and receive antennas with the consideration for isotropic power we are going to see. So here wherever we write a subscript or a suffix r, that resembles in order to identify whether it is a transmitting or a receiving. If I write r, it is your receiving. If I write t, it is your transmitting. So the free space transmission is also denoted in decibels, and the right side equation, which is PR is equal to EIR P EIRP is your equivalent isotropic radiated power plus GR, which is gain in the receiver, minus the free space transmission loss, which is minus 10 log 4 pi r the divided by lambda the whole square. Okay, so this right hand side, which is EIRP, is your transmitter, GR is your receiver, and minus 10 log 4 pi r divided by lambda the whole square is your free space transmission losses. So now let us calculate this free space loss component in decibels. Why we are writing negative of that is that this is a loss. It is to be removed. So we are writing minus there. So the free space loss component in decibels is given by 10 log 4 by r divided by lambda the whole square. So where lambda can be obtained by the carrier frequency and c value is the velocity of light and lambda can be obtained from that. So r would be your distance in kilometers, which is measured. So we get free, free space loss component as 32.4 plus 20 log r plus 20 log f. In this ratio we'll get. So கருப்புல தட்டுற நாலு தின்னாருன்னு நினைக்கிறேன். கேளுங்க கேளுங்க எங்க அப்பா கேளுங்க அப்பதான் சொன்னாரு சொல்லிட்டு. Then the received power will be in this equation. PR is equal to EIRP plus GR minus FSL. So let us see a problem. So the range between a ground station and a satellite is 42,000 kilometer we assume, and calculate the free space loss at a frequency of 6 gigahertz. Frequency of 6 gigahertz. So take this equation which you had seen earlier, 32.4 plus 20 log r plus 20 log f. 32.4 plus 20 log the distance r is the distance 42,000 plus 20 log 6,000. Always we should write a measurement of f in megahertz. So, right? 6,000. So we get 200.4 decibels. If you want, you can make a manipulation of flow. Next loss is feeder loss, which is at your receiver.
The first sign like
So next parameter is feeder loss. So this feeder loss will occur in connection between the receiving antenna and the receiver segment. So the losses that occurs in the connection between the receiving antenna and the receiver segment. So this losses will occur in the places where we connect waveguides, two different waveguides, same waveguides with filters or couplers or any feeding points. So this is denoted by RFL measured in decibels. So this RFL or the receiver feeder losses can be added with pre-space losses also. After the feeder losses, we'll see the antenna misalignment losses. So when a satellite link is established, satellite antennas are aligned with earth station to get maximum gain. Satellite antennas will be aligned with the earth station for getting maximum gain, such that the satellite antennas will be focused towards the earth station antenna with its axis. So there could be two possible losses. One is off axis, which is at the satellite, and another one is off axis at earth station. So due to this alignment in antenna occurs. So we will keep antenna in one direction, that will turn out in another direction. So the satellite link, which is established, should focus towards each other, both at the satellite as well as at the earth station. So depending upon its positioning and axis, the losses occurs. If they are in tight in a straight line, and if they focus with each other, there will be no moment of access. Okay. So the misalignment losses can be avoided. So if alignment is lost, we get an alignment loss. So the off-axis loss at the satellite is taken into account by designing the link for operation on the actual satellite contour. And the off-axis loss at the earth station is referred to as antenna pointing loss. Antenna pointing loss, which is pointed at the earth station. So in addition to the pointing losses, there could be losses that are being obtained at the antenna from the misalignment of polarization direction. So always this polarization misalignment losses will be very small, denoted by AML. So this antenna misalignment loss will have both pointing and polarization losses, which together gives antenna misalignment loss, which we write in short AML. So antenna misalignment loss will have two things. One is pointing loss, antenna pointing loss, and antenna polarization direction loss. So this is your diagrammatic representation. So satellite and earth station aligned for maximum gain. You can see this is your ground station at the earth, and the antenna is focused towards the satellite. So the direction from satellite to the earth is same. There is no misalignment, or we can call that the satellite and the earth station antennas are aligned for maximum gain. Whereas here when you see diagram B, the earth station is given at a satellite. You can see earth station situated in a given satellite footprint is out of alignment. You can see that. You can see the maximum beam alignment. So these are misaligned. So earth station misalignment angle we call with respect to the earth station, and a half beam width angle for given satellite footprint contour. Antenna misalignment losses. So after the antenna misalignment losses, we get fixed atmospheric and ionospheric losses. Ionospheric, the ions in this atmosphere tends to absorb some part of the signal of which we are transmitting in uplink and receiving and downlink. So the gases does the phenomena of absorption. So this absorption results in ionospheric losses. So they diffract, they scatter, they absorb, as well as they transmit also. So which is denoted by AA, atmospheric absorption. So these losses usually amount to a fraction of a decibels, and they are being denoted by a symbol notation AA. So AA and 90-degree cosecant EL. So the ionosphere introduces a depolarization loss. The decibel value for this will be PL. Okay, depolarization loss. PL is equal to 20 log ECO divided by E, which is 20 log cos theta F. So now the link power budget equation. The power at the receiver, which is the power output of the link, may be calculated by this. Link power budget equation can be calculated by EIRP minus losses plus gain at the receiver.
அப்பா இல்லன்றப்பா நீ போனா கொஞ்சம் கேக்குமே நான் அது இருக்குதுன்னா நான் போறேன்
நான் கேஸே கூட்டி போறேன். EIRP minus losses plus
கையெழுத்து யாரும் நான் போறேன் அவன் எக்ஸ்பிளைன் பண்ண
plus GR. So when the last GR is the receiver antenna gain. So the major source of losses in any ground satellite link is the free space spreading loss, FSL, free space transmission losses. So the basic link power budget equation taking into this losses only is written here. So, however, we cannot neglect the other losses also. So the losses that we had seen is that free space loss, receiver feeder loss, antenna misalignment loss, absorption, atmospheric absorption, and depolarization loss. So all this comes under your losses. So the decibel equation for the received power would be received power. PR is your received power will be EIRP plus GR, which is a gain in the receiver, minus losses. So substitute all those things, we get it here. So these are the expansion of each and every parameter that we are wrote. Yeah, received power, decibel watts, EIRP equivalent isotropic radiative power, decibel watts, free space spreading loss or the transmission loss, decibels, receiver feeder loss, decibels, antenna misalignment losses in decibels, atmospheric absorption loss in decibels, PL polarization mismatch loss or the depolarization loss in decibels. Let us see an example such that you can understand what this link power budget equation is and how this plays a major factor or a major role in satellite space link. A satellite operating at some frequency, so the frequency given is 14 gigahertz, has some feeder loss. Keep in mind, feeder loss is RFL, receiver feeder loss, which is 1.5 decibels, and a free loss of 207 dB. Keep in remembrance what is this free space, FSL. So free space loss of 207. And there is an atmospheric absorption of 0.5 AA and antenna pointing loss, which is which is AML, antenna misalignment loss, which is 0.5. And they are given that depolarization loss is neglected. It is very small. So calculate the total link loss for clear sky conditions. For a clear sky condition, calculate the link loss. So add all the losses, you get it. So to 1.5 plus 207 plus 0.5 plus 0.5, we get 209.5 decibel losses for a space link operating at 14 gigahertz. So any queries till this? Design in the link power budget, determining losses. And still further, we need to discuss about the noises being introduced. Okay, I'll give you 2 or 3 minutes time. If there is any queries, put in chat box. Then we'll proceed further in discussing about the system noises. Since I couldn't find any queries in the chat box, I'll proceed for the next parameter, which is used for designing your space layer, which is system noise. The receiver power in a satellite link is very small. Whatever the power we receive in your satellites, so that is very small, so which is in the order of picowatts. So this by itself would be having no problem, because amplification could bring into effect, which will increase the signal strength up to an acceptable level. So during this process of upgrading the signal strength, we get some noises which we call it as electrical noise, which is defaultly present due to the electrical equipments which are present for amplification. So however, this electrical noise is present, and unless the signal is significantly greater than the noise, amplification will be of no help, as it will amplify the signal and noise to some extent. So in fact, the situation will degrade by the noise added by the amplifier also. So the major sources of electrical noise in the equipment is that it arises from random thermal motion of electrons in various resistive and active devices in receiver. Random thermal motions. And how does this thermal noise is generated? This thermal noise is generated in the lossy components of antennas and is being picked by the antennas as radiation. So due to this also, thermal noise may occur. The main characteristics of this thermal noise is that it has a flat frequency spectrum, which is noise power per unit bandwidth, which remains as a constant. So for this we need to find the noise power spectral density, so which is N0 is equal to Pn by Bn, which is K into Pn into measured in joules G. So the noise temperatures of various sources which are connected together will be added directly to give the total noise. So now let us see the total noise calculation with an example. Keep in mind these formulas. In system noise, I forgot to. So the system noise arising due to thermal noise is given by Pn is equal to K Tn Bn. So N suffix or its subscript is always your noise component. So Tn is known as the equivalent noise temperature which arises in the satellite due to that noise. So Bn is the equivalent noise bandwidth, the bandwidth in which that noise has been generated. So K is your Boltzmann constant. Take the constant value 1.38 to 10 power minus 23 joules per Kelvin. With the temperature in Kelvin and bandwidth in the hertz, noise power in watts. Okay, so this is your thermal noise. So now let us see a problem on this. An antenna having a noise temperature of 35 Kelvin, which is matched to a receiver having noise temperature of 100 Kelvin. Calculate noise power density and noise power bandwidth. So, and the required bandwidth that they are asking is for 36 megahertz. So now substitute noise power density. So noise power density is this N0. Noise power density is N0 is equal to Pn by Bn, which is K Tn measured in joules. So K. So here we have two temperatures. One is antenna temperature as well as receiver noise temperature. So antenna has a noise temperature of 35 Kelvin and the receiver has a noise temperature of 100 Kelvin. So add both of them. So we get 135 Kelvin. So this is how to calculate the equivalent, because Pn is the equivalent noise temperature, not the particular. So equivalent will be summation of these two. So equivalent noise temperature will be 35 plus 100 Kelvin, which is 135 Kelvin, into the Boltzmann constant K, 1.8 into 10 power minus 23, which gives 1.86 into 10 power minus 21 joules, which is noise power density. Next, we need to find Pn. Pn is K, Tn, Bn. So K, T, N. Already we had found. It is 1.86 into 10 power minus 12. Sorry, minus 21. And Bn, which is the bandwidth in hertz, is 36 megahertz. So 36 into 10 power 6 we get. The noise power for the bandwidth of 36 megahertz as 0.067 picowatts. 0.067 picowatts. So this is how to find noise power density and noise power for a bandwidth of certain frequency. So noise power density and noise power for a bandwidth of 36 megahertz is found. So in addition to this thermal noises, we have another parameter to be considered, which we call it as intermodulation noise. In the satellite system, satellite link design system. In designing of the satellite link design, we need to consider this noise also, which is intermodulation distortion. So this occurs in high power amplifiers and results in signal products which appear as noise and referred to as intermodulation noise. So they are, what are they? How do they occur? Antenna noise, amplifier noise temperature, noise factor, noise temperature of absorptive networks, overall system noise temperature. So let us see the first antenna noise. Let us see antenna noise. So antenna noise are being introduced by satellite receive antenna and the ground station receive antenna. The satellites receive signals from a transmitting earth station, that one, and the ground earth station which receives the signals from the satellite, that one. So due to that we get antenna noises. So although the physical origins of the noise in either cases would be similar, noises would be similar, but magnitudes of effects, the magnitude ranges will differ significantly. So hence they are classified into noises originating from antenna loss, noises originating from antenna losses, and sky noise. So classifying them into two: antenna losses, noise, and sky noise. So we had seen about antenna noise. So now let us see about the sky noise. So sky noise, this arises due to the attenuation of a wave Since it is dealing with space, it is electromagnetic wave. So sky noises appears due to the attenuation of a wave when it passes through the atmosphere. When it passes through the atmosphere. So this attenuation may be due to atmospheric gas, rain, snow, galactic, etc. So noises which are being generated by any of this. So when a signal passes through the, or when electromagnetic wave passes through some gases, so there is those gases gives attenuation. When it passes during rainy season, it gets attenuated. In snowfalls, it gets attenuated. During galactic or anything. So due to attenuation of the electromagnetic wave, due to all this is called as sky noise. And most probably the galactic noise effect is below 1 gigahertz. The equivalent noise temperature of the sky would be as seen by the Earth station antenna. So we are calculating with respect to that. So this is sky noise. So you can see the galactic noise region, low noise region, and the tropospheric noise region. So it is being divided into frequency in gigahertz. Up to 1 gigahertz, we get galactic noise region. And the antenna noise temperature can vary till 10,000 Kelvin, at 10,000 Kelvin. And as it goes to the frequency in between 1 gigahertz to 10 gigahertz, we get noise temperature to be as lowered. So you can see that noise temperature is lowering. So as from 10 gigahertz to 100 gigahertz, the noise temperature also increases again. So there is a Gaussian curve in nature. So and at some points it increases both in oxygen resonance as well as in water power resonance. So this is why we choose the frequency of transmission in either uplink and downlink in between 1 gigahertz to 10 gigahertz. Okay, due to the sky noises. So the region between 1 gigahertz to 10 gigahertz is considered to be as low noise region, whereas below 1 gigahertz we get galactic noise region, about 10 gigahertz we get tropospheric noise region. So the design of the satellite should be falling in and around this 1 gigahertz to 14 or 16 gigahertz, because at 22 gigahertz we have a water vapor resonance. You can see that water vapor resonance is present at 22.2 gigahertz, and during 60 gigahertz we get oxygen resonance. So you can have a view on this. So any queries, put in chat box. So since I couldn't find any queries for this topic, I move on to the next topic, which is antenna losses. So the antenna losses add to the noise received as radiation, and the total antenna noise temperature is the sum of all the equivalent noise temperatures of these sources. So for larger ground-based antennas, C-band is used. So ground-based C-band antennas is used, which is typically about noise temperature is typically about 60 Kelvin. And for the KU band antenna, if you use KU band antenna, it is about 80 Kelvin. So under clear sky conditions, keep in mind it is under clear sky conditions. C-band antennas, 60 Kelvin noise temperature, and KU band, 2-band antenna, it is 80 Kelvin. So accordingly, we need to design the satellite for better propagation. You can see the noise temperature is varying from 0 to 60 in y-axis, and in x-axis we have 0 to 50 of the antenna elevation angle. Okay. So what happens is that we choose polarization as linear polarization, operating frequency in between 11.7 to 12.2 gigahertz, the gain of at 11.95 gigahertz, measuring about 45. So at this, at 10-degree elevation, we get 10-degree elevation, we get around 47 Kelvin noise temperature. At 20-degree elevation, we get 35 Kelvin noise temperature. At 30-degree elevation, we get 32 Kelvin noise temperature. And the VSWR measurement maximum we get 1.3. Isolation decibel loss of 35. Half power beam width measured in degrees 0.91. And the pattern envelope PE number 4374. So this is just an example of noise temperature versus the antenna elevation angle. If the elevation angle of the antenna changes with respect to the satellites, how it affects on the noise temperature. Okay. If it is 0, it is 0. At 0-degree elevation, there is no. At 0-degree elevation, it is 0. So next is amplifier noise temperature. So how do I calculate noise temperature due to an amplifier being present inside the satellite? So this is the input noise energy coming from the antenna, which is noise. So N naught coming from antenna. So comma antenna. So which is KT. So K is the Boltzmann constant. T is the noise temperature of the antenna. And output noise energy is N out. Okay. Noise is your N naught. Out is the output noise. So N naught comma out is equal to G N naught of antenna. The gain in the antenna, noise in the antenna, plus contribution made by the amplifier. So whatever the amplifier is contributing for noise generation is contribution made by amplifier. So N naught and out will be GK gain. K is the Boltzmann constant. Transmit antenna plus E, which is a T out. So the total noise referred to this input is simply N naught out by G, or N naught in, which is K into Boltzmann constant K into T antenna plus T. So this is your amplifier noise temperature structure. You can see. First diagram is an equivalent noise temperature measurement of an amplifier. We have T antenna, we have N naught, we have in for an amplifier. Then N out naught is the output. And then we are doing cascading. So cascading can be done like this. Output of the first is fed to the input of the next. This is how to calculate. So for cascade collection, for cascading, G is equal to G1 into G0, G2. G1 is the gain of the first amplifier, G2 is the gain of the second amplifier. So the noise energy of the amplifier is referred to its input, simply KT2. So we get the noise energy due to amplifier 1 by dividing available power gain of amplifier 1. So N naught 1 is equal to N naught comma 2 divided by G1. So where N naught 2 can be obtained by G1 K T antenna plus TE1 because due to first plus K TE2. So on simplifying, substituting it in N naught comma 1, we get K into T antenna plus TE1 plus TE2 divided by G1. So this can be expanded for any cascade or any number of stages in cascade. So TS is equal to T antenna plus TE1 plus TE2 by G1 plus TE3 by G1 G2 and it goes on. So amplifier noise temperature. Usually we choose a low noise amplifier. So the design is given for that. So any queries you can put in chat box. For this amplifier design structure. So since there are no further queries, I move on to the next topic, which is noise factor. So an alternative way of representing the amplified noise is by means of a noise factor F. So the definition of the noise factor of amplifier is taken at room temperature, denoted by T naught. So the room temperature is 290 Kelvin. Okay. So the noise input from such a source is K into T naught, and the output noise from the amplifier is FGK T naught. F is the noise factor, G is the gain, K is the Boltzmann constant, T naught is the room temperature. So a simple relationship between the noise temperature and noise factor can be derived. So let T be the noise temperature of the amplifier and room temperature is T antenna is equal to T naught. So we can get GK T naught plus TE, which is F GK T naught. So TE is equal to F minus 1 into T naught. So the noise figure is simply represented in decibels, which is noise figure. F is represented as 10 log F. So we have a problem based on that. So a low noise amplifier, which is a LNA, is connected to a receiver having a noise figure of 12 decibel, gain of 40 decibel, and noise temperature is 120 Kelvin. So calculate overall noise temperature, which is referred to low noise amplifier input. So 12 dB is a power ratio of 15.85 is to 1. So therefore, it can be expanded as 15.85 minus 1 into 290, which is 4306 Kelvin. So a power gain of 40 decibel is a power ratio of 10 power 4 is to 1. So therefore, 120 plus 4306 divided by 10 power 4. We get T in and TE2. Next is noise temperature of absorptive networks. An absorptive network is one which contains resistive elements which are introduced by absorbing energy from signal and converting it to heat. So there is an additional noise temperature to be measured. So which consists or which is observed due to resistive element. So the noises introduced by the loss of absorbing energy from the signal and converting it into heat. So these are due to the resistive attenuators. These are due to resistive attenuators, transmission lines, waveguides, which are the examples of absorptive networks. So the absorptive networks creates noise temperature also. So as said in the first 2 or 3 slides, a transmission line, a waveguide, a OFC cable, or any copper cables are used for transmission, and some couplers, attenuators, or feeders are being used. So due to that, we get some absorbing energy that is produced by the heat of them. So which comes under absorptive networks, noise temperature. So this is a noise temperature of an absorptive network. We have the ambient temperature during the transmission. We have a RT, a terminating resistor at one end and an antenna at the other end. So I consider both the networks are matched at both the ends with the lossy network power loss of L is to 1. So we get ambient temperature Tx. So the noise generated by this absorptive network can be obtained by this design equation. N radians is equal to radiated noise at radiated energy n radians is equal to K Boltzmann constant Tx is the ambient temperature. Ambient temperature is the nominal temperature being measured, or the desired temperature for the efficient satellite link communication, divided by L plus K T NW comma naught. So the equivalent we get T N W comma naught is equal to Tx 1 minus 1 by L. Equivalent noise will be equivalent noise of the network will be NWI is equal to Tx L minus 1. We get that the room temperature at room temperature, the noise factor of a lossy network is equal to its power loss. You can see that. So now let us see the overall system. Overall systems noise temperature. Okay. So the overall system's noise temperature can be written as Ts. So system temperature. So Ts is equal to T antenna transmitting antenna losses due to that, losses due to the TE1 plus L1 L minus 1 T naught divided by G1 plus L into F minus 1 T naught by G1. So the connections used in examples illustrating overall noise temperature of the system. So due to this L is to 1 condition, we get G1 and F. So this can be done for cascading also. So next topic we have the propagation effects on the satellite system. We have the satellite link design. We have the propagation effects and the propagation and their effects. What are the atmospheric absorption, cloud attenuation, the geometry of satellite path for rain attenuation, the depolarization and the atmospheric losses. So this we'll discuss in the next class. So if you have any queries, type in chat box. Any queries till this, you can type in chat box. So the propagation effects on satellite system will be taken in the tomorrow's class.